This morning I'm talking to one of our senior engineers, Valentin, and our topic today is the differences between low pressure casting processes and counter pressure casting processes. Valentin has a lot of background in this and a lot of knowledge, and I'm hoping today that he can teach me all about it. So good morning, Valentin.
Good morning, Nick.
Okay. You want to pull up your presentation and let's talk about it.
Today we will make a comparison between casting processes today, low pressure and counter pressure. Low pressure is quite popular. I will highlight the main features of the process. We have a machine with a vertical opening of the plates. We have a mold with a horizontal parting line. Beneath the mold we have a furnace with liquid alloy, and through the riser tubes we move the alloy to the cavities, holding the pressure a little bit until solidification. Then we release the pressure in the furnace. Then we can open the mold and get the parts out of the mold.
Valentin, what's the typical gas that's used in this process?
We use air, dried air.
It's just basically air. And
yes.
There's no risk of diffusing anything into the liquid aluminum? Or?
First we remove the moisture. So we use the dried air, and of course we have a contact on the top of the alloy, grabs some amount of hydrogen, but thanks to the substances on the top, and we can grab this hydrogen isolated from the alloy, and it cannot penetrate deeper in the alloy. Counter pressure process. On the first glance, it is almost the same. On the left side, you can see traditional low pressure mold. On the right side, you can see counter pressure. But only on the first glance, because we have a main difference here. In counter pressure, we have the mold inside the chamber where we have additional pressure. This is our additional dimension to the casting process.
Valentin, same question now on the gas. Are we using dry air again as the counter pressure?
Yes, exactly.
Same thing. So we're really pressurizing the mold.
Exactly, yes.
So two separate sources of air pressure, one on the liquid aluminum and one on the mold.
Actually, it is the same source, but we split on two flows, one to the furnace and one to the chamber.
Okay. And does this requirement to pressurize the mold make design changes or design features in the mold to help it seal better?
Yes, it needs some new features in the mold in order to keep the pressure and create this counter pressure in the system. I will give you more details on this configuration.
Okay.
So again, the mold is surrounded by a chamber, and we have another pressure in this chamber. This is actually the counter pressure. In the beginning of the cycle, with the pressure in the furnace and the mold with the same value from the same source, we just pressurize the whole system. Then we start to create pressure difference between the mold and furnace, and we make the lower pressure on the furnace a little bit higher than pressure in the mold. That means that we can move the alloy up yard to the cavities and start filling them. Once we have solidified parts, we can remove the pressure and open the mold to get the parts out. We have some minor stages inside this process, and I will give you details after a while. We will start with a deeper explanation on the counter pressure process. We have a pressure from the top which goes inside the cavity through all the gaps that we have in the mold, between ejector pins and the upper cavity, between the vent pins, in the parting line, and every single split line in the mold can provide actually this pressure inside the cavity, and it faces the pressure from the bottom, from the furnace. So we have double graph in the plot on the right side. The red line is pressure of the mold and blue is pressure in the furnace.
Y-axis is pressure in millibars. Okay, that makes sense. And then time in seconds below. So it looks like you're showing there for this example a cycle time of just about 160 seconds, something like that.
Yes, exactly. The whole cycle time is 240 seconds because we have some time with zero pressure to solidify the parts further and to be able to eject them out of the mold.
Oh, okay, yeah. I see the extension of the blue line along the x-axis. Yeah. Okay.
At this stage, the things really gets quite a bit theoretical because we have many specifics in this process, which I would like to explain, and also to explain the advantages that we have in counter pressure versus low pressure. First advantage is that the pressure that we have on the top, the alloy, doesn't allow during the filling to have splashes, fontaines, turbulence in the alloy, and we have much better control of the filling this way. In this way, we can avoid grabbing additional amount of hydrogen in the alloy and then to create some non-metal inclusions inside the structure, which is a really good thing. The second advantage that I want to highlight is that the filling and most of the solidification process happens in the absolute pressure in the system. We can use whatever we want, 2000 millibar or 3000 or 1000 millibar. We can set this pressure very easily on the machine. In the practice, we normally use 2000 millibar. So we start from this point, the filling of the part. That means the alloy is pressurized. Now we have a really big advantage. We cannot have hydrogen evolved in small bubbles inside the alloy because we push it and it stays dissolved in the alloy. This helps a lot to remove the microporosity in the microstructure after that, and really helps to improve the mechanical properties.
That's interesting to me. So the contrast there between low pressure and counter pressure, effectively in a low pressure process, the pressure is really just used to ease the metal into the die. So there's no extra pressure there inside the
Exactly.
The whole process is taking place at a higher pressure, and then all the benefits coming from that.
We can shift the 0 point in the system, having the counter pressure, so everything happens in a different media, air with high pressure, which is a main difference if we compare with the other processes.
Yeah, so presumably that then all of those benefits that leads to better mechanical properties of the casting. So two identical castings made from low pressure versus counter pressure, the counter pressure casting will have higher performance.
Yes, all of the other casting processes take place in atmospheric pressure. Only counter pressure happens in higher absolute pressure, which is a good thing, and this is the main difference if we compare to the rest of the casting processes. So we have this shifting up. We can choose the value, how much to shift. It depends on the strength of the machine. Of course, we can shift up to 5 or 6 bars. From, let's say, one definite value up, we have not so significant advantages of the high pressure. So we normally use 2000 millibar to start casting.
When looking at a low pressure casting machine, can it be converted to a counter pressure casting machine, or is it completely different?
Theoretically, yes, modifications. Since this process needs hermetical chambers around the molds, in many cases it's not possible on the machine once made, because we have to avoid some treat holes, some channels, some other features on the machine that's difficult to seal.
So I should really think about it as two separate machines.
Yes, and also we have to add one more unit to control the counter pressure. The next advantage that we have, it's maybe the most theoretical part of this explanation and presentation, because it's a little bit difficult to visualize and to imagine. But we have this moment in the process when metal solidifies, it shrinks, you know this. Shrinking means a deficit of the volume. And if we have a closed system, this deficit of the volume means creating the vacuum. So we have this in our system when we solidify the alloy, but in the same time we have high pressure still acting in the liquid alloy, and thus we can smash the semi-solid crystals in the alloy, and this way we can have this microplastic deformation. This is the right term. So it helps a lot to compress the structure and to reduce the natural porosity almost completely. This is also a unique option of this process. It takes place in a moment where we still have high pressure in the chamber for the mold, and we can prolong this stage as long as we need, but need to be careful with the solidification of the sprue to not plug the riser tubes. However, everything is easy to set, so we can find the right settings and to have this effect in utmost degree and to have this profit of action, which mainly results in lower volume of the risers or even no risers. Also, it results in better feeding of the thick sections of the part.
Explain that to me again, Valentin, why there would be a smaller riser with this?
Because we can push more material to build the structure of the solid part, thanks to this microplastic deformation. So that means we don't need so big volume of the risers, or even in many cases we can avoid the risers.
Because you can deliver more liquid aluminum to the cavity.
Yes, and particularly in the border between solid and liquid phase of the alloy.
Okay. Yeah.
Where the things happen, it moves, and we building the solid structure all the time until we have solidified the whole volume of the part. So during this process, we have this microplastic deformation, which is really helpful to achieve better mechanical properties.
Yeah, so you're really explaining microscopic level what's happening that produces the benefits, the mechanical properties benefits, and this is happening on the border between the solid material and the liquid material as that progresses through the casting. Yes. Yeah.
Yes.
Okay.
Let me highlight another advantage. Because we can shift the 0 point in this process, we use media with high absolute pressure. In our case, this is dry air, and this air is much denser and thicker than in atmospheric pressure. So we have 2 bar in my example, 2 bar on the pressure. That means the density of the air is much higher, and the heat transfer between the alloy and the mold is much better. You know already that this gives us an advantage regarding to the speed of solidification, finer microstructure after that, higher mechanical properties, and shorter cycle time. Additionally, we have this counter pressure inside the pores of the coating. The coating actually is a number of small ceramic grains on the mold wall. So we have this fighting against filling pressure, and this way counter pressure doesn't allow aluminum to copy exactly the surface of the mold, and we have smoother surface and less defects on the skin of the part.
All as a result of that extra pressure.
Yes, the fifth advantage, but we have a long exposure of the high pressure in the whole system, so liquid alloy, thanks to the microplastic deformation, can feed the thick sections much better than other processes, and we could have combination with thin walls, thick walls. And normally, if we cannot achieve zero porosity with this configuration on low pressure, in most of the cases, with some design tricks on the mold, we can have zero porosity by using counter pressure. Okay, my final sheet just CPC process has unique features no other process has. We can achieve really high mechanical properties because of the zero natural porosity and faster solidification that we have. Microplastic deformation helps to fit the heavy sections in the part better, even through thin walls. When we make knuckles suspension parts, we very often have this problem to fit thick walls and bosses through thin walls, and CPC helps a lot in this case. Another thing that we have is better control on the filling, because we work on both ends on the alloy, from the bottom through the furnace pressure and from the top through mold pressure, so we can avoid splashes and turbulence during the filling. Also, we have a smoother and stronger skin because counter pressure acts inside the cavity in the coating and fight again the filling pressure, so the alloy cannot copy exactly the surface of the mold this way. What we can benefit from the chamber is that we have safer working environment and no danger to spill the metal and somebody to be hurt. Everything is closed, so it's really safe regarding to the other processes. And this also helps to keep the heat inside. We have more stable process. More heat inside means, in most of the cases, shorter cycle time, a lot of other advantages. And last thing that I would like to mention is that we even can use sand molds, because for the filling of the cavity, we use only differential pressure, not absolute pressure. So we could have 2 or 3 bar absolute pressure in sand mold, and it will not destroy the sand mold, because the filling pressure is only the difference between lower and upper. This way we can use sand molds in this process. This is also unique. Thank you, Nick. If you have questions, please.
Yeah, our audience should realize, I think, this short presentation, that you have some significant experience around counter pressure. Maybe just tell me about that. How many years have you worked with counter pressure processes?
Starting 2004 till now.
Okay, and you have both theoretical and practical knowledge, correct?
Yes, exactly.
So my point being there for our audience is, if they would like to know more about counter pressure processes, who contact us and we can set up some discussions. If they've got problems, please reach out to us. You fully understand the design requirements of the tooling associated with these processes also. Is that correct?
Yes. Yes, exactly.
Anderson Global, we're capable of building those tools, and we do today build counter pressure tools.
My experience in the foundries, I often see people that neglect the difference between low pressure and counter pressure, and they say it is the same, it doesn't work to use counter pressure. Hopefully this presentation will make many people to think that it is not the same, because it is really not the same. We have additional dimension in the process.
Yeah, and the castings produced have improved material properties.
Exactly. Yeah.
And I think in an environment here in the United States, as we move towards electrification, lightweighting, looking to take weight out of vehicles, obviously the ability to give a product designer the ability to make smaller cross sections and lower weight components and still meet the strength requirements, this could be part of an answer to do.
Yes, you are right. Some of the automakers even have a requirement to the suspension parts to be made only under pressure, not low pressure. So this also means that we have significant advantages from counter pressure.
Okay, great. If anybody would like to learn more, please reach out to us. And this will be on our YouTube channel with a bunch of other videos that show some of our technical capability. So thank you, Valentin.